I first would like to remind you of the central limit theorem that we discussed in the previous lecture, and we solved exercises on it. Remember what it says. We will do the following. So it says that so first you have a population, as you can see here. This is my population, and this is my sample. And you know that in inferential statistics, what we usually do is from the population, you choose a representative sample, and then you use the sample statistic that you compute. We are doing the sample mean in this case, and you use it to infer something about the population mean. This is one of the things of inferential statistics, one of the things that inferential statistics help you do. You can also do it from the sample standard deviation to get to know things about the population standard deviation. Okay, and so now I want to remind you of the central limit theorem of the last lecture. It said that if your population has any distribution, it doesn't matter. But as long as your sample size, you choose a sample size that is bigger than or equal to 30, then you can apply the central limit theorem. It works in this case. Okay, that was the first part. But what does it say after? Okay, so we are able to apply the central limit theorem, but what does the central limit theorem say? It says that your distribution of sample means, x bar, is going to follow an approximately normal distribution. Okay, and the second part of it that we took as a second part, okay, was that if you started with sorry for this. So if you started with a normal population, a population that is normally distributed, then it doesn't matter whether your sample size is less than 30 or bigger than 30, the central limit theorem is going to work. And so this is what it means, but it will be precisely normal. So there is no approximately normal here. It will be precisely normal. A question that you might ask, like, when doesn't it work? Can you guess before I put it? So if we have what, then we cannot apply the central limit theorem. Easily, you can see that if you start with any distribution and then you take a sample that is less than 30, then you cannot guarantee that the central limit theorem is going to work. It will fail in most cases. Okay, so this is just a review of the central limit theorem. Let's now see what we will do. But before we see it, I just want to remind you that the central limit theorem, if it's okay, you see, if it works, then we know that the distribution of sample means, x bar, will be approximately normal. This means, by the way, that everything that you see here on the horizontal axis is an x bar of some sample. Okay, but you need to choose samples of the same size. So let's just say that we take samples of size 30 or more. You can take 36. You know, when you take samples of size 36, it makes it easier to do calculations, because when you do the standard deviation, look, this will be sigma over radical 36, but we know radical 36 is 6. So it's just an easier number. Okay, so I suggest that when you choose samples, just choose 36 to make the calculations easier. Remember also that we saw that the mean of the sampling distribution of sample means is the same as the population mean. Okay, so mu of x bar, so the mean of sample means is the same as the population mean. In this lecture, please always remember that this will be an unknown for us and we want to find it in this lecture. Okay, in the previous lecture it was given to you. Also remember the standard deviation, which also we called it the standard error of the mean. Remember what is a standard deviation? When you go down, it's exactly one step away from the mean. So you have 1, 2, 3 standard deviations to the right, and 1, 2, 3 standard deviations to the left. But what's important is, what is this standard deviation? You compute it by taking the standard deviation of the population and divide it by the square root of the sample size. Okay? This is just a very, very quick review of central limit theorem and what it told us.